Have you ever wondered why a simple garden hose, with just your thumb over the end, can shoot water so far?
Mm-hmm.
Or maybe how a massive hurricane can literally cause the ocean to swell up. It's kind of amazing.
Yeah, it really is. And today, we're taking a deep dive into exactly that, the very core of how fluids move.
Right. Whether it's air, water, gasoline.
Pretty much anything that flows. And we're focusing on three really powerful foundational equations from fluid mechanics.
The conservation of mass.
Yep, the Bernoulli equation.
And the general energy equation. Okay.
That's right. And our source material is it's a detailed textbook chapter. Our mission today really is to pull out the most important bits.
Give you a shortcut? Kind of.
Exactly. A shortcut to being well-informed about fluid flow, mechanical energy, and, why this stuff actually matters in the real world.
Think of it like an expedited tour, maybe, through the big ideas engineers use for everything from, wind turbines.
Yeah, or even just simple siphons.
Right. So our aim is to sort of demystify these concepts, maybe find some surprising facts, and help you understand not just what these equations are,
but why they're so critical, why they really shape how we see the physical world.
Okay, so where do we start?
Well, let's kick off with one of nature's most fundamental principles, the conservation of mass.
Okay. Seems almost obvious, doesn't it?
Yeah.
Mass isn't created or destroyed.
It feels obvious, yeah. But it's profound. Like you said, it's like balancing a checkbook. What goes in plus any change inside has to equal what comes out.
So how does that simple idea play out with fluids, which can seem so dynamic?
Well, the key thing to grasp is this. While mass is always conserved, volume isn't necessarily conserved.
Ah, okay. How so?
Take an air compressor, you've got air going in, air coming out. The mass flow rate, the kilograms per second passing through, is constant.
Right.
But the volume flow rate at the outlet, it's much less.
Yes, it's compressed.
Exactly. The air density is higher. Same mass, smaller volume.
And we see this even with something like a garden hose nozzle, right? The source had a good example.
A really good one, yeah. Imagine you're filling, say, a 10-gallon bucket. Takes 50 seconds.
Okay.
Now, if you put a nozzle on that hose, shrinking the diameter from maybe 2 centimeters down to just 0.8 centimeters.
The water speed's way up.
Dramatically. The average velocity in that example jumps to 15.1 meters per second.
15.1.
That's fast. It really is. What's surprising is that this simple nozzle makes the water go over 6 times faster than in the hose itself.
6 times?
Yeah, roughly 34 miles an hour. From a garden hose, it's just a perfect everyday example of keeping mass flow constant through a smaller area forces higher velocity.
And this conservation principle holds even when things change over time, like water draining from a tank.
Absolutely. The source had an interesting bit on that too, a 4-foot high tank. Emptying the top half, so from 4 feet down to 2 feet, takes about 12.6 minutes.
Okay, 12.5 minutes.
But emptying the entire tank from 4 feet down to 0, that takes 43.1 minutes.
Wow, that's much longer. So the bottom half takes way more time.
Way more time. And the critical question is why?
Right.
It boils down to the decreasing water height edge. As that height drops, the pressure pushing the water out decreases.
Less push.
Less push means the discharge velocity slows down significantly. It's not a linear process at all. That last bit of water really takes its time leaving.
Okay, so we've got mass flow sorted. What about the energy involved, the power behind the flow?
Right. That brings us to mechanical energy. This is the energy form that can be directly converted to mechanical work.
Like kinetic energy motion and potential energy elevation, we know those.
Yep. But in flowing fluids, there's a crucial third component.
Which is?
It's called flow energy. Mathematically, it's pressure divided by density, P over rho.
P over rho. Okay, flow energy. Why is that mechanical?
Because it's tied directly to the pressure forces in the fluid doing work as the fluid moves. Pressure acting over a distance is work.
Got it. And this helps explain things like pumps and turbines.
Exactly. Pumps add mechanical energy to a fluid. They usually increase its pressure, maybe push it uphill.
While turbines do the opposite. They extract mechanical energy.
Right. They convert the fluid's energy maybe from pressure drop or falling elevation into useful work, like spinning a generator.
But in the real world, it's never perfect, is it? There are always losses.
Never perfect. You always have irreversibilities, mainly friction.
So that energy doesn't just vanish?
No, it converts. Our source mentions efficiency, say a pump is 74% efficient. That means 26% of the mechanical energy you put in isn't doing useful work on the fluid.
It's turning into heat.
Exactly. Frictional heating. It actually causes a slight temperature rise in the fluid. It's why we talk about pump efficiency, turbine efficiency, motor efficiency, generator efficiency. They all quantify how much energy is lost, or rather converted.
Okay, let's put some numbers on that. The hydroelectric example.
Yeah, good one. Imagine a lake, 50 meters higher than a turbine. Water flows at 5,000 kilograms per second.
Okay, big flow.
The fluid itself ideally supplies 200 and 455 kilowatts of mechanical power to the turbine.
2.5 megawatts, roughly.
But let's say the generator connected to the turbine is 95% efficient.
Which is pretty good, actually.
It is good, but you still only get 1,862 kilowatts of electric power out.
So we lost almost 600 kilowatts, somewhere between the water hitting the turbine and electricity coming out.
Well, lost isn't quite right. It's converted. In this case, for the whole turbine generator system, about 24% of the initial fluid power ends up as heat due to inefficiencies.
Wow, that's a lot of energy just warming things up slightly.
It highlights why efficiency is absolutely critical in engineering design, especially at large scales. Every percentage point matters.
Okay, that makes sense. Now, what about this Bernoulli equation? It sounds important, but maybe a bit intimidating.
It's incredibly powerful, yes, but maybe simpler than you think. It gives a direct link between pressure, velocity, and elevation in a flowing fluid.
But there's a catch, right?
Yeah.
It's an approximation.
A very important catch. It comes with strict conditions. And honestly, understanding the limitations is just as crucial as knowing the equation itself. You misuse it, you get bad answers.
Okay, so what are the conditions? Lay them
Yes.
out for us.
All right, first, steady flow. Conditions at any fixed point can't change over time. The fluid can speed up or slow down as it moves, but at one location, it's constant.
Got it. Steady. What else?
Second, incompressible flow. The fluid's density has to stay constant. Works great for liquids.
And gases.
Good for gases too, but only at relatively low speeds. Technically, Mach numbers below about 0.3, so not for supersonic jets, for instance.
Okay. Steady, incompressible. Number 3.
Third, and this one's key, negligible viscous effects, or sometimes called inviscid regions.
Does that mean the fluid has no friction?
Not quite.
Yeah.
It means the internal friction forces, viscosity, are so small compared to the other forces, pressure, gravity, inertia, that you can basically ignore them.
So it works well away from walls, maybe.
Exactly, not right near a pipe wall or in the wake behind an object where friction is dominant.
Okay. And the last one.
Fourth, it applies along a streamline. Strictly speaking, it follows the path of a single fluid particle, though in some special cases, it can apply across streamlines too.
Right. Understanding those limits is key to using it properly.
Mm-hmm.
Now, you mentioned pressure, velocity, elevation. Can we break down the terms in the equation?
Yeah, absolutely. If you look at the equation, each term actually represents a type of pressure or energy per unit volume.
Okay.
First, there's just P, the static pressure. That's the actual thermodynamic pressure of the fluid, what a regular gauge measures.
Simple enough.
Then there's a term,
Yeah.
1/2 rho V squared. That's the dynamic pressure.
Dynamic, meaning it relates to motion.
Precisely. It represents the pressure rise you'd get if you brought the fluid to a complete stop smoothly, converting all its kinetic energy into pressure energy.
Okay. Static, dynamic, what's the third?
The third term is rho OG is E. That's the hydrostatic pressure. It accounts for the potential energy due to elevation, the weight of the fluid. And the sum of the static pressure and the dynamic pressure is called the stagnation pressure. That's the pressure at a point where the fluid is brought completely to rest.
Stagnation point. Okay. So how do we actually measure these things? You mentioned a pitot tube.
Right. A pitot tube is a clever device used for exactly this. It has an opening facing directly into the flow, which measures the stagnation pressure.
Okay.
Then, usually nearby, there's another opening, a static port, flush with the surface, which measures the static pressure, P.
Ah, so you measure both.
Yeah. And the difference between the stagnation pressure and the static pressure is exactly the dynamic pressure.
And from that, you can calculate V, the velocity.
Exactly. The source gives an example. If the pressure difference corresponds to a 12-centimeter height difference in a connected water column,
Then the velocity is.
you calculate it out to be 1.53 meters per second. It's a fundamental way flow speed is measured in airplanes, wind tunnels, pipes, all over the place.
That's really neat. So we can visualize this flow too, right, with those lines, HGL and EGL.
Yes. The hydraulic grade line, HGL, and the energy grade line, EGL. These are super useful visualization tools.
How do they work?
You take the Bernoulli equation terms, but instead of pressure units, you divide everything by rho times g, or sometimes just g. This gives you units of length, or head.
Like height.
Exactly. So you get pressure head, pug, velocity head, v to g, and elevation head. The HGL is a line showing the sum of the pressure head and the elevation head, pug plus z. It represents the height water would rise to in a little vertical tube tapped into the flow.
Like a piezometer.
Precisely. And the EGL represents the total mechanical energy head, pressure head plus velocity head plus elevation head, pug plus v to g plus c.
So the EGL is always above the HGL.
Always. By exactly the amount of the velocity head, v to g, it visually shows you the kinetic energy part.
What can these lines tell us? What's their behavior?
Some interesting things. In a big, still reservoir, the EGL and HGL are flat and match the water's surface level, since velocity and gauge pressure are 0.
Makes sense.
As fluid flows through a pipe with friction, both lines slope downwards in the direction of flow. That slope represents the energy loss.
The head loss we talked about earlier.
Exactly. And if you have a pump,
They jump up.
sharp jump upwards in both lines because energy is added.
And a turbulent.
Sharp drop downwards, energy is removed.
Okay, this is cool. But what's the most practical thing they show?
Maybe this. You can instantly tell if the pressure inside a pipe is below atmospheric pressure or vacuum just by looking at where the pipe is relative to the HGL.
Ow.
If the pipe itself is above the HGL line at any point, the pressure head there must be negative. The pressure is below atmospheric.
Whoa. And that's bad.
It can be very bad. That's where you risk cavitation. If the pressure drops below the vapor pressure of the liquid, it can start to boil even if it's cold, forms vapor bubbles.
Which can damage pumps and things, right?
Which image pumps choke the flow.
Yeah.
Yeah, it's something engineers work hard to avoid. The HGL is a direct visual warning for potential cavitation zones.
Fascinating. Let's connect Bernoulli back to some real examples. The garden hose jet height.
Right. The source revisited that. If the pressure inside the hose is 400 kilopascal.
Which is, what, about 60 psi? Pretty typical.
Yeah. Bernoulli predicts the water jet could theoretically reach a maximum height of 40.8 meters.
40.8 meters. That's like 130 feet, 13 stories.
Theoretically, it gives you the absolute upper limit, ignoring air resistance and jet breakup.
Which are obviously huge factors in reality.
Absolutely. But it sets the ideal performance boundary.
Okay. What about siphoning gasoline? That always felt a bit like magic.
It's not magic, it's physics. It's driven by the pressure difference between the surface in the tank and the outlet, thanks to gravity, not suction, really.
Right. And Bernoulli can analyze it.
It can. The source example. Siphoning 4 liters of gasoline, density 750 kilometers, through a small 5mm hose, with the tank surface 0.75 meters above the outlet.
How long does this take?
Minimum time, according to the calculation, is about 53.1 seconds.
Okay. But didn't you mention a pressure issue with siphons?
Yes, this is critical. In that example, the highest point of the siphon tube is 2 meters above the gasoline surface in the tank.
Oh.
Using Bernoulli, the pressure calculated at that high point is only 81.1 kilopascals.
Which is well below normal atmospheric pressure, around 101 kPa.
Exactly. If that pressure drops below the vapor pressure of gasoline at that temperature, poof.
Bubbles form.
Bubbles form, the liquid column breaks, and the siphon stops working. Cavitation again. There's a limit to how high you can lift the liquid in a siphon.
Wow. Okay, now the hurricane example. That seems like stretching Bernoulli a bit. No, hurricanes are so turbulent.
It is an approximation, definitely. Applying it to such complex, unsteady, turbulent flow is not strictly valid. But it gives a surprisingly good estimate of the ideal limit for the storm surge caused by the pressure drop and the wind.
So how does it break down?
2 main effects. First, the extremely low atmospheric pressure at the hurricane's eye.
Yeah.
The source example goes from standard pressure, around 30 inches of mercury, down to 22 inches.
That's a huge drop.
Huge. Just that pressure difference causes the ocean level to rise by about 8.83 feet in the eye. It's like an inverted barometer effect.
Okay, almost 9 feet just from low pressure. What about the wind?
The high winds, 155 miles per hour in the example, exert dynamic pressure on the water surface. Using the dynamic pressure term from Bernoulli gives an additional rise of about 0.70 feet.
So nearly another foot just from the wind pushing down, essentially.
Kind of, yeah. It contributes to the total swell. So Bernoulli gives us an idea of the combined effect, around 9.5 feet in this idealized case.
And it's important to remember that this isn't the only factor in hurricane flooding, right?
Absolutely not.
Hmm.
You have waves on top of the surge, heavy rainfall, and the surge interacting with the coastline topography. But Bernoulli helps quantify those core pressure and wind effects.
Okay, so Bernoulli is powerful, gives us great insights and upper limits, but it ignores friction and real devices like pumps.
Exactly. For the full picture, especially when losses are significant or you have machines involved, we need the general energy equation,
The big one.
the big one. It's basically a more comprehensive statement of the conservation of energy, accounting for everything.
Including that energy lost to friction.
Precisely. It introduces a term called head loss, usually written as HL. This specifically represents the mechanical energy irreversibly converted into thermal energy due to friction in pipes, valves, bends, etc.
So HL is friction's energy tax, basically.
That's a good way to put it. And it has a direct consequence, temperature rise.
Right, you mentioned that earlier. How does the general energy equation handle that?
Well, it relates the energy states at 2 points in a flow, including any energy added by pumps, removed by turbines, H turbine, and lost to friction, HL. In adiabatic flow, no external heat transfer, any mechanical energy loss, HL, must show up as an increase in the fluid's internal energy, which means a temperature increase.
Even if it's tiny.
Even if it's tiny. The source had that pump example. A 15 kilowatt motor, 90% efficient, pumping 50 Ls of water. About 3.5 kilowatts of power was lost to friction within the pump and fluid.
And the temperature rise what?
A minuscule 0.017 degrees Celsius.
Wow. Barely measurable, but it's there. Proof the energy didn't vanish.
Exactly. It's a fundamental check. Energy is conserved, just transformed. And you can't have temperature decrease in steady adiabatic flow with friction that would violate the second law of thermodynamics. You can't spontaneously create mechanical energy from low-grade heat.
Okay. How does head loss, HL, impact something like hydroelectric power again?
Let's revisit that. Say you have a 120-meter elevation difference for your hydro plant, but due to friction in the long pipe, the penstock leading to the turbine, you have an irreversible head loss of 35 meters.
So you've lost 35 meters of potential energy-driving force before the water even reaches the turbine.
Effectively, yes. That energy has turned into heat in the pipe flow. So an ideal turbine without pipe losses could generate, say, 83.4 megawatts.
But with the 35-meter loss.
And adding in, say, an 80% overall efficiency for the turbine and generator, the actual electric power output drops to 66.7 megawatts.
That's a significant drop, almost 20% less power just due to pipe friction and system efficiency.
Huge impact. Minimizing head loss is paramount in designing these systems.
Okay, there was one other factor mentioned. This alpha thing. Kinetic energy correction.
Ah, yes. Alpha, the kinetic energy correction factor. It's a small refinement.
What's it for?
Basically, when we calculate kinetic energy using the average velocity VG in a pipe, it's not perfectly accurate because the velocity isn't actually uniform across the pipe. It's usually faster in the center, slower near the wall.
That's the velocity profile.
Alpha corrects for that. For smooth, slow laminar flow, alpha is actually 2.0. For the much more common turbulent flow, it's much closer to 1, usually around 1.05 or so.
Does it matter much in practice? If it's only 1.05?
For most turbulent flow problems, honestly, no. The kinetic energy term itself is often small compared to pressure and elevation terms, so multiplying it by 1.05 doesn't change the result much. Engineers often just assume alpha is 1.
But sometimes it is important.
In cases with very high velocities where the kinetic energy term is large, or specifically when dealing with laminar flow, then yes, ignoring alpha or using the wrong value could lead to noticeable errors. It's for precision work, mainly.
Good to know. Okay, let's wrap up with some practical design examples using the full energy equation. Cooling a computer.
Yeah, kind of a neat small-scale application. To completely replace the air inside a typical computer case, say 9,600 cubic centimeters every second.
Needs a fan, obviously.
Needs a fan, but the actual useful mechanical power that fan needs to impart to the air is tiny, only about 0.152 watts.
That's minuscule.
It is. Now, if the fan motor unit is only 30% efficient,
Which is maybe typical for a small, cheap fan.
probably, then the electrical power drawn is still only about half a watt, 0.506 W. And the pressure rise needed across the fan is incredibly small, just 15.8 pascals.
Wow. So these big principles scale way down.
They really do. Another example, pumping water up to a swimming pool.
Okay.
Say you have a 5 kilowatt pump and it's 72% efficient. It needs to lift water 25 meters vertically.
Plus overcome friction.
Right. Let's say there's 4 meters of head loss, HL, in the pipes and fittings. Taking all that into account, the pump can deliver about 12.7 liters per second.
Okay, 12.7 Ls. How much difference does that head loss make?
Well, if you magically had zero head loss, perfectly smooth pipes, no bends, etc., that same pump could deliver 14.7 liters per second.
So that 4 meters of head loss costs you about 2 liters per second.
Yep, about a 16% reduction in flow rate in this case.
That really shows why engineers care so much about minimizing friction losses in piping systems. It directly impacts performance.
Absolutely. Every bit of head loss requires more pump power for the same flow rate, or gives you less flow rate for the same power. It's always a key design consideration.
So quite a journey today. We've really unpacked these core equations, conservation of mass,
Bernoulli's equation, with all its power and its important limitations.
and the general energy equation, which accounts for the real-world complexities of friction and machines.
And hopefully, we've shown how they form this incredibly powerful framework for understanding how fluids behave everywhere, from, like you said, garden hoses.
Hydroelectric dams,
Yeah.
and even getting a handle on something as complex as a hurricane's storm surge.
They really are the language engineers and scientists use to describe and predict the flow of liquids and gases.
It's amazing how these seemingly abstract principles are just so deeply tied into the physical world we see and interact with every single day.
Mm-hmm. So maybe the next time you see water flowing or feel the wind.
Or even hear your computer fan whirring.
Yeah. Think about that unseen dance of mass and energy, pressure, velocity, elevation, friction, all constantly interacting and transforming according to these rules.
It definitely gives you a new lens to see things through. So, a final thought for everyone listening. What other everyday things can you now look at and see the hidden fluid mechanics at play?
That's a great question to ponder. Keep curious.
Absolutely. Keep exploring the fascinating world of science and engineering. Thanks for joining us on this deep dive.